Welcome to Module 3 on Applications of Trig Functions. In this set of notes, we'll be looking at solving trig equations. We will be covering the sine and cosine laws as a way to set up and solve application problems using trig equations. Let's talk about how to solve a trig equation and what it involves. What we're attempting to do is find the values of a particular variable that satisfies the equation. Because of their periodic nature, trig equations have an infinite number of solutions. Normally, you'll be given a range over which you would like to find a solution. In this course, we will solve trig equations for values of x from 0 to 360 degrees inclusive, and we'll be rounding our final answer to the nearest tenth of a degree. Just a reminder that when you're solving trig equations using your calculator, to make sure that if you're looking for your answer to be expressed in degrees, to make sure that your calculator is in degree mode, whereas if you would like to express your final answer in radians, your calculator should be in radian mode. Now we will look at an example of solving a trig equation. We're given that 5 times sine of x is equal to 3. We want to find the value of x that satisfies this equation. The first step is to rearrange the equation for sine of x. To do so, we divide both sides of the equation by 5. Now this simplifies to sine of x is equal to 3 over 5. And 3 over 5 can be expressed as a decimal of 0.6. Now to solve for x, we take the sine inverse of both sides of the equation, and we find that x is equal to sine inverse of 0.6. Your calculator will only give you one solution in this case. We end up getting 36.9 degrees. Now we can take a look at how that looks graphically by looking at our Sine X curve. So shown here is the function y is equal to sine of x, where your x-axis is given in degrees. Up until now, the majority of our axes have been labeled in pi radians. What we are looking to solve for is all the values of x such that sine of x is equal to 0.6. If we mark 0.6 on our y-axis, we want all these values of x where the value of y is equal to 0.6. And you can see because sine of x is a periodic function, there would actually be an infinite number of solutions. And the one that was found in our calculator is this very first value of 36.9 degrees. Although there are an infinite number of solutions where sine of x is equal to 0.6, we want to only report the solutions between 0 and 360 degrees. Although we know one solution for x of 36.9 degrees, to find the second solution, we must use the cast rule. The cast rule tells us where the trig functions cosine, sine, and tan are positive. Given our unit circle, so we have 360 degrees here, we could label the angles, so separating each of the quadrants, 0 degrees, 90 degrees, 180 degrees, and 270 degrees. And then when we've made one full circle, we have 360 degrees. To label the cast rule, we start in the fourth quadrant in the lower right-hand corner. And we label that C, then A, S, T, finishing off in quadrant 3. These letters tell us where each of the functions is positive. In quadrant 4, cosine is positive, but all other trig functions are negative. In quadrant 1, all of the trig functions are positive. In quadrant 2, only sine is positive, and in quadrant 3, tan is positive. So to summarize for the sine and cosine functions, sine is positive in quadrant 1 and quadrant 2, and cosine is positive in quadrant 1 and quadrant 4. Therefore, sine is negative in Q3 and Q4, and cosine is negative in quadrant 2 and quadrant 3. We can examine a particular angle in quadrant 1. We can call this angle alpha. Alpha is defined as an angle from standard position, so from 0 degrees up to alpha degrees. We can show the same angle alpha for each quadrant. Now we want to express each of these angles as angles from standard position. In quadrant 2, we can express the angle as being 180 degrees minus alpha degrees. In quadrant 3, we get 180 degrees plus alpha, and in quadrant 4, we get the angle shown as 360 degrees minus alpha. The cast rule allows us to find other solutions to our trig equations. So looking at our last example again, if we have y is equal to sine of x, which is shown as the red curve, we can look at all the values of x within the 0 to 360 degree period where sine of x is equal to 0.6. So we mark 0.6 on our axis, and we can see that it occurs at 2 different points. Right here, and then another one just shy of 150 degrees. And using our cast rule to determine what those actual angles would be, we know that sine of x is positive in the following two quadrants. So it's positive in the second quadrant as well as the first quadrant. Given that alpha is equal to 36.9 degrees, that's the angle determined from our calculator when we solved sine of x is equal to 0.6, we can find the second angle, alpha, over in the second quadrant by taking 180 and subtracting alpha. Therefore, if our first solution is at 36.9 degrees, our second one will occur at 180 minus 36.9 degrees, and we get 143.1 degrees. Therefore, our second solution is 143.1 degrees, and that's the second solution solely within the range of 0 to 360 degrees. Solving trig equations requires practice. It requires a lot of comfort with your sine and cosine home functions, as well as the cast rule to solve trig equations. Let's work through some examples together. The first question is solve 4.5 times sine of x is equal to negative 1.3. And we're asked to express all solutions between the range of 0 and 360 degrees. The first thing we want to do is consider solving the equation 4.7 times sine of alpha is equal to 1.3. By making all the values positive, it forces the angle that we find to be found within the first quadrant, and you can note that in the cast rule, alpha is always an angle within the first quadrant, so it will be between 0 and 90 degrees, not inclusive. Now divide by both sides of the equation by 4.7 in order to solve for sine of alpha. We need to get sine alpha by itself before we can solve for alpha. So sine of alpha is equal to 1.3 divided by 4.7. Now to solve for alpha, we take the sine inverse of both sides of the equation, and we find that alpha is equal to sine inverse of 1.3 divided by 4.7, which is equal to 16.1 degrees when we round to the nearest tenth of a degree. This gives us our angle of alpha within quadrant 1, but what we were looking for are the angles where sine is negative, because we end up with negative 1.3 divided by 4.7. So looking at our cast rule, C-A-S-T, starting to label from the lower right-hand corner, we know that sine is negative in quadrant 3 and in quadrant 4. Now we need to express our angles in the third and fourth quadrant, given that alpha is equal to 16.4. So in quadrant 3, we know that x is equal to 180 plus alpha, which works out to be 196.1 degrees. And in quadrant 4, we know that x is equal to 360 degrees minus alpha, which is written as 343.9 degrees. Therefore, our solutions for x between the range of 0 and 360 degrees are 196.1 and 343.9 degrees. Now you might be wondering if these answers are in fact correct. What you can do is check your answers. To check your answers, you take each of the angles that you calculated as solutions and plug them into the original equation, and if you evaluate the left-hand side, you should find that 4.7 times sine of x for each of your x values is in fact equal to negative 1.3. With the next example, we have that cos of x is equal to negative 0.5431. We want to force the initial angle that we find, alpha, to be an angle within quadrant 1. To do so, we consider cos of alpha is equal to 0.5431. When we solve for alpha using our calculator, we find that alpha is equal to cos inverse of 0.5431, which is equal to 57.1 degrees. Now, although our angle in the first quadrant is 57.1 degrees, using the cast rule, we want to determine where the angles are that we can use to solve our initial equation. The initial equation has cos of x being negative, and we know that cos of x is negative in quadrant 2 and in quadrant 3. Therefore, the respective x values would be 180 minus alpha, and that works out to be 122.9 degrees. And the other angle to consider is in the third quadrant at 180 degrees plus alpha, which is 237.1 degrees. Therefore, our two solutions within the range of 0 and 360 degrees are 122.9 and 237.1 degrees. In example 3, we want to find the value of x that satisfies 5 times tan of x minus 6.8437 is equal to 0. To solve this, the first thing we want to do is get tan of x by itself. Steps we need to solve for that are to first move our constant to the other side of the equation, and it becomes positive. Then we divide both sides of the equation by 5. And we find that tan of x is equal to 6.8437 divided by 5, and x is equal to tan inverse of the same. When we initially solve this equation for an angle, I should have called it alpha here, within the first quadrant we find that alpha is equal to 53.8 degrees. Okay, which this is a value with it is already in the first quadrant, and looking at our cast rule, we know that we're looking for values where tan is positive. We know that it's positive in quadrant 1 as well as in quadrant 3. So we already have an angle here in quadrant 1. This is in Q1. So we need to find an angle in the third quadrant. Therefore, our angles work out to be x is equal to 53.8 degrees, and the other angle is 180 plus 53.8, or plus alpha, at 233.8. Don't forget to check these solutions by plugging it into the initial equation. Now pause the video, try the next 3 questions, and then watch the video to see the solutions. In the next video, we'll look at different techniques to solve application problems involving trig equations.